Welcome to the second and last lecture about change detection algorithms. So today we're going to cover some advanced ones, probabilistic advanced ones. Okay, so the first thing that we are addressing is the issue that we have when the variable we want to test is not a scalar, but it is a vector. So in the previous lectures, we had the t-student, the chi-square test, the f-test. They were all assuming that the variable z is a scalar. So the mean is a scalar, and the variance is a scalar. But when z is a vector, things are different, because the mean of z is a vector itself, and its variance is no longer a scalar, but instead it is represented by a matrix that is called a covariance matrix. One way to build a probabilistic test for a variable that is a vector is to consider its multivariate distribution. So instead of considering independently the distribution of each component of z, we consider them together. So this is a multivariate distribution case. One way of doing that is to introduce what is called the Mahalanobis Distance. So this difficult name here. Well, to understand the Mahalanobis Distance, the best thing to do is to have a graphical introduction, because then it is quite easy. So if we have a variable z that is a vector, as we said, the mu, the mean of the variable, is a vector. So in 2 dimensions, it is a point here. This is mu. And the covariance, we said, it is a matrix. So if we look at the matrix, well, we can compute vectors, eigenvalues, and eigenvectors. And if we are in 2 dimensions, there are 2 eigenvectors. One, let us assume, is this one. And it is the one associated to the bigger eigenvalue. The other is this one, associated to the smaller eigenvalue. Well, it turns out that if you consider all the possible values of z, so if you draw a lot of samples of z, and if you look at those samples, you get a cloud, and this cloud, unsurprisingly, has the shape of an ellipse. And the major axis of the ellipse is the eigenvector with the biggest eigenvalue. And the minor axis of the ellipse is the other one. So this shouldn't be too much surprising. Well, now the question that the Mahalanobis distance is asking is, okay, given a value of one sample, like this one, is this sample far or not from the mean? Well, if we consider the case where this ellipse actually is a circle, so the 2 eigenvalues of C are the same, answering the question whether this is close or not to the mean is simple. So we take the distance between the sample and the mean, that is, we compute the 2 norm of this vector, and this is telling us whether we are far or not. And far or not actually depends not only on the distance itself, but also on the variance. So if a random variable has a big variance, it is quite normal for samples to be far away from the mean. If the variance is small, then all the samples are close to the mean. So actually taking the distance alone is not so much informative. But If you take the distance and if you divide it by the variance, and if you look at this normalized distance, well, this makes more sense for a random variable. So you remember that in one dimension, for a Gaussian variable, you have that 99% of them, of the samples, are no farther away than 3 sigma from the mean. So in one dimension, we could say, if you have a normalized distance, distance over variance, that is no more than 3, you are close to your mean. Otherwise, you're far. Okay. We could adopt this idea for a variable that is multivariate and take the distance and normalize it by the variance. The only issue is that in multiple dimension, there is not just one variance. We have a matrix describing the covariance. And in this case of the ellipse, actually you see immediately what is the meaning of having a covariance matrix. Because if we are moving away from the mean along this direction, before we can say that we are far away from the mean, we need to walk a lot. Because all along this direction is quite normal for a sample to be far away. If we move along this direction, then even after a relatively short walk, we are already far away. Because along this direction, we know there is not so much variation. So that eigenvalue of the covariance matrix is small. So the idea of the Mahalanobis distance, actually, it is to introduce a way of normalizing the distance that takes into consideration that along different directions, different distances have different meaning. So along the direction of big variation, you want to normalize the distance in a different way than along directions where you don't have so much variation. And indeed, the Mahalanobis distance is doing this. How? The Mahalanobis distance is computing d of z, the Mahalanobis distance of z is computing the square root, as in a Euclidean distance, we take the square root, of this quadratic form. In a normal Euclidean distance, you would have, when you have vectors, z minus m, so the distance, this is z minus m, this vector, transpose that multiplies itself, which is the way of taking the square of this vector. This in the Euclidean distance. In the Mahalanobis one, you normalize by the covariance. But as the covariance now is a matrix, what you end up is that you multiply here in the middle by the inverse of the matrix. The good thing, before you worry about, is that you always have the inverse here, because C is positive definite, well, semi-definite. There is also another interesting interpretation about the Mahalanobis distance. The interpretation is like the one with the bullseye, the target that you hit. So if you plot the loci of the points that have an equal value for the Mahalanobis distance, you get ellipses that are all centered around the mean. So then, it is easy to tell whether a sample that you got is far away from the mean or not. You just check, okay, inside which of these ellipses are you? So remember, in the Gaussian case, one dimension, if you are inside the circle that is equal to 3, you are no farther than 3 sigma away from the mean, so you are good. And the same thing you can apply to the Mahalanobis distance. You can find a limit value for D, which we call the overbar, that tells you whether you are safe or not. So for instance, we can say, well, This is the maximum value for D that we accept. So the ellipse that has a distance equal to D over bar is bounding all the values of the samples of Z that I get in nominal conditions. So if my sample is inside, I confirm the null hypothesis. If it is outside, I reject the null hypothesis. So how is this D over bar determined anyway? It is determined using the Chebyshev inequality. It is an inequality for random variables that is going to tell you when you can consider that a random variable is nominal, a sample of that is nominal, and when not, assuming only knowledge of the mean and the covariance of that random variable. So without knowing the PDF. So in the tests that we have seen in the previous lecture, so the t-student, the chi-squared, the f-test, we assumed to have the PDF and then also to have the CDF. And the threshold was based on that, on the CDF. In this case, we don't even need to know that. We just need to know what is the nominal mean and the nominal variance of the random variable Z. So the nominal mean and the nominal variance anyway shouldn't be a surprise, are the values that we use here to compute the Mahalanobis distance. So you start from the knowledge of the nominal mu and the nominal c. You use it to compute the Mahalanobis distance of each sample that you get. And then the threshold is simply this ratio here, n over alpha. So n is the dimension you are in. So in this case, it is 2. And alpha, again, is such that 1 minus alpha is your significance level. Because indeed, if you set the threshold d over bar in this way, then the probability of the distance of a sample under the null hypothesis being bigger or equal than d over bar is smaller or equal than this alpha. So what you can do is, for instance, to set alpha to 1%. Then the probability of having a sample here or here is less than 1%. And this is the way to implementing then a probabilistic test using the Mahalanobis distance and the Chebyshev inequality for the multivariate case. So this approach has some advantages and some disadvantages. Well, the obvious one is that you can address the multivariate case. Another advantage is that you don't need to know what is the PDF of the variable. The disadvantage is this inequality here, that is the Chebyshev inequality, is quite conservative. So actually, the false alarm rate that you can get when you apply this is way better, but can be also order of magnitudes better. So in practice, what people are doing is, instead of using this inequality to define the threshold d over bar, they are just determining it from data. This means that in healthy conditions, you get a lot of samples. You compute mu and c, which usually you need anyway to compute from data. And then you determine what is an acceptable level for d over bar, such that less than some percent, 1% of healthy data in your data set is outside this ellipse. Now let's go back to the general case and let us address one other shortcoming of the probabilistic test we have seen before. in particular, the unsatisfying compromise between high significance and high sensitivity of the test. And to get better tests, we're going to introduce a new quantity. Well, maybe you already heard about that, but a quantity we did not use before, and it is the log likelihood ratio. So let us assume that your variable z has a PDF that is parameterized, and it is parameterized by a parameter theta. And this theta is the thing that is changing. In the example we have seen in the previous lecture, theta was the mean or the variance. So theta has two possible values, theta 0 and theta 1, before the change, after the change. And theta 0 is the nominal. So given a single observation, a single sample of z, we can compute a quantity that is called the log likelihood ratio this way. So the likelihood, given a sample of a random variable, the likelihood is the value of the PDF computed for that sample. But in this case, the PDF is parameterized. What we do is to compute the ratio between the two likelihoods, one under the null hypothesis and one under the alternative hypothesis, the one after the change, and then we take the logarithm of that. Well, one good thing of the log likelihood ratio is that, well, itself, it is a random variable, of course, because this is a random variable, and when you compute the function of a random variable, you still have a random variable. So we can compute the expectation of S. The expectation of S is equal to this expression if we are under the null hypothesis, and this expression if we are under alternate hypothesis. Well, the good thing is that the expectation here and here, they have different signs. The first one is negative, and the second one is positive. Why? Because let us look at S here. S here, if you are under null hypothesis, is going to be the logarithm of a ratio which is smaller than 1. Why? Because under null hypothesis, the probability of here is higher than the probability here. So the ratio is smaller than 1, and the logarithm is negative. If you take a quantity that is always negative, and you compute this integral, and the probability that you have here is always a number is always positive, then the result is negative. So by definition, this is always positive. So we are sure this is negative. And the other way around is also holding. So if we compute, so this was under null hypothesis. If we compute the expectation under alternative hypothesis, then this is positive. And it is easy to see why. Under alternative hypothesis, the term at the numerator here is bigger than the term at the denominator. So this is going to be bigger than 1, so the logarithm is positive. And again, we have an integral of only positive quantities. This is positive. Okay. So I guess that already you see here the potential to build up a change detection test that is very powerful, because now we have two quantities and we know they have different signs. So it's quite easy to check that. And let us see indeed how to do that. The way to do that actually is not just to compute them and check if they have positive or negative sign, but to compute a running average over time. In particular, to compute a cumulative sum over time, which is like an average but without normalization. And why we want to do that? Well, the thing is that this is a random variable. So if you have a given sample set, you cannot compute these exactly. You can only compute the expectation over that sample set. You can approximate that by computing the empirical mean over a sample set. This is the only thing that you can do. And it turns out then to be a random variable again. So as it is random, you have noise, and it is not very robust to compare a noisy value to a threshold. I mean, it is the entire story we are talking about, so we can do better than just evaluating one single sample of the empirical mean in this condition or this other condition against 0. And this is the rationale for the cumulative sum. So instead of looking at S and taking the empirical mean over a time window and so on, what we do in this case is to have a running sum, a cumulative sum of S, which we remember, we write it again here again, is the logarithm of this likelihood ratio. Well, then, during moments that we are in the null hypothesis, so under the null hypothesis, this most of the time is negative. When we are under the alternative hypothesis, this most of the time is positive. So the behavior that we expect is, assuming this is the moment we have a change, so here we have the parameter taking the value θ1, and here we have the parameter taking the value θ0. What we expect is that the cumulative sum S, capital S of k, is going down here and up here. Indeed, because here we are summing, adding negative terms to the sum, and here we add positive terms to the sum. If you look really, really carefully, there would be moments where, for a very short period, even under null hypothesis, you sum positive terms. But as this is just due to measurement noise and other uncertainties, we expect this to be short-lived. Instead, when we have a change that is permanent due to a fault, for instance, then the positive trend will stay for a long period. So, if we look at the cumulative sum long enough, we expect to see this V shape when we have a change. Then we moved the problem of detecting a change in the variable z to detecting this change in the cumulative sum. And to detect this change, we need yet another test. And the test is based on this decision function, g. So d is equal to what? To the actual value I have of the cumulative sum, s of k, minus the quantity m of k. And m of k is the minimum value that we got of s until that moment. So when we go down, s and m most of the time are the same. But after a change, m will stay constant, while s will increase. So if we look at the difference between s and m, if we look at g, let's make another plot here. G is going to be pretty much small, and then after the change, it is increasing. Okay, at this point, what we just need to introduce is a threshold for G. And we call this H. So when G is bigger than H, it means that we are in this ascending phase of the cumulative sum. So anyway, quite a long way. So we start from Z, we need to know two things: the probability under theta 0, the probability under theta 1. We compute S, the log likelihood. We compute capital S, the cumulative sum. We compute the minimum so far, M. We compute the term G. And finally, we test if it is bigger or smaller than H. Detect. Why are we doing all of this? Well, because these turns out to have better performances in terms of misdetection rate and false alarm rate and detection delay than other tests. And this is an example I have taken from the book by Blanke about applying these to a Gaussian variable. So if you have a Gaussian variable, the probability under the hypothesis that the mean is equal to mu is equal to this one. If you take the ratio between the two probability under the hypothesis that the mean is mu1 or mu0, you get this expression here with an exponential. And now you see why people is using the log likelihood. Because when you have Gaussians, then by taking the log likelihood of this ratio, then the exponential goes away. So in the end, S is equal to this expression. And so you see, it is not so much more complex than the t-student variable we use in the t-student test. If we have, for Gaussian variables, a change in both mean and variance, then the expressions are going to be this. But in the end, well, the complexity of the expression for S is not so much different. Anyway, we were able to compute that for the Gaussian case because we have closed form formulas for the PDF that are not so much complex, and we were able to do some simplifications and substitutions. If you have a general distribution, then there is possibly no way of writing S here as a closed form. But this is not so much important as long as we can approximate this numerically. There are ways to approximate distributions that are known. And if we have a good way of determining the value of H for this test. All right, okay. There is a very big, possibly hidden problem in this approach. Well, one issue is that we assume that we know mu0 and sigma 0. And this is not so bad, because they correspond to nominal conditions, so we probably know them. But the formula for the CUSUM also implies that we know the post-change values mu1 and sigma 1. And this is quite a big assumption, because it is like saying I know exactly which kind of fault is occurring to my system. And also, if this fault can occur, let's say, small and big, I know exactly how big. But this is quite a lot of assumptions, and in practice, you don't have this information. Even if we make the simplified assumption that there is no change in variance, still, mu1, the post-change mean, is a parameter that we need to estimate from data. We don't know it. And finally, H is a parameter that we need to tune. And this is controlling the compromise between robustness, significance of the test, and sensitivity of the test. Because you can imagine that if H is small, I have a lot of false alarm here during nominal conditions. If h is big, well, I don't have these false alarms, but it is taking a lot of time for this ramp to cross it. And if the fault is intermittent, and after some time we go back down like this again, maybe I never cross the threshold. Okay, so how are we solving this issue? Well, there are a few options. One option is that we replace mu1 with the minimum change that we want to be able to detect, or we can estimate it from data. There are both advantages and disadvantages. So if we use a minimum change that we want to detect, this is going to reduce our sensitivity. Why? Let us look at this example. So we have here, well, not S of k, sorry. This is G of k. Okay. We have G of k here. And then we have the nominal PDF, which is a Gaussian, which is centered around 0. And then we have the true faulty, the post-change distribution here, that is centered around, I guess, 2. Now, what happens if I set as a minimum value for the post-change mu? Not 2, but something bigger. So let's say 3. Then I have this other PDF here. Well, this is going to influence the sensitivity of G. In our case, this sensitivity means how fast G is increasing. Let us see. If we have the pre-change PDF, and if we knew exactly the post-change PDF, assuming that at some point we get this sample, this value of the sample here exactly in 2, the likelihood under the true post-change hypothesis is quite big, but under the nominal hypothesis, this is small. So when I compute the log likelihood ratio, this is a big number, big positive number, and so G is going to increase, and in general, G is going to increase, let's say like this. But if as a post-change PDF, I'm using the green one, then the likelihood of the green one for the same value of the sample is smaller. And the log likelihood ratio also, because we have the ratio now between this and this, which is smaller than the ratio we had before if we knew exactly mu1, this between this and this. So when I'm using the green curve, the G is going to increase at a lower rate because the individual terms in the summation are smaller. So this approach is causing a sensitivity that is not so good, because for the same h, the detection delay is longer here. Another approach would be, okay, we continuously estimate mu from data. But then it means that we need to have time windows. We need to have 2 time windows to estimate the pre-change, or where maybe that we know. We need to have a time window to estimate the post-change. If we want to be accurate, this window needs to be long. If this window is long, then again we have detection delay. So it looks like that detection delay will always be there in a way or the other. The other thing that we need to tune is, we said, h. So how do we tune the threshold h over which the function g is compared? Well, if we have Gaussian variables, we can do it exactly. You have seen before in the example that we can write out closed form expression for the CUSUM in the case of Gaussian variables. So we can solve a problem where we optimize for h, and we get the optimal h. So you can see something on the book by blank at these pages from 244 to 246. But if we have a general distribution, or in practice, still, we can tune H in an empirical way. What we can do is to take data in nominal conditions and try to tune H such that we don't have too much false alarms. And for instance, this is a plot which shows, as a function of H, what is the average time between false alarms. And as you can see, the higher, the better. So if I have a higher average time between false alarms, I have few false alarms. You see, anyway, the increase, I don't remember from which case this is taken, but the increase is not linear. But I want also to try to optimize the other side of the coin, to optimize the sensitivity. In this case, I want to have a short detection time. And to do that, I need to generate some artificial data under faulty condition. So I need a way to generate offline data simulated in a nominal condition of the system and non-nominal condition of the system. And then I can run my algorithm with different values of H, and I get different values of the detection time. So the issue is that both cases, the optimization you do are for a specific system under specific operating conditions. And in this case is also for a specific fault. And if the fault is parameterized, for a specific value of the parameter of the fault. So you see, if you want to consider all the possible conditions of your system, then you need to do a lot of simulations. And in the end, probably you will have to sit with a compromise either. Another approach to solve the shortcomings of the CUSUM based on the log likelihood ratio is to use another test that is called the Generalized Likelihood Ratio test. So we generalized the previous one. And the aim of the GLR is to take the same CUSUM as before, but now we want to estimate both the post-change parameter θ1 and the change time k0. And the way this is done is solving a maximum likelihood estimate problem. So we take the CUSUM S and we want to maximize it. Because you remember, after a fault, a change, well, the S, or anyway G, they are increasing. And also we have shown here that the better is our estimate of the post-change parameter mu, the faster is the increase. So a way to find the mu, that is the best one, is to maximize S by changing mu. So if we maximize S over mu, then we get a mu1 that is closer to the true post-change value. But, yeah, here in general we have a parameter θ. So if we maximize over θ1 the sum, well, the argument of the solution of this is the best estimate θ1 hat of the true post-change value θ1. But similarly, also getting the correct change time is making this term bigger. So when we maximize these, we can have another problem running around that when we maximize the result of this on the change time instant. So basically, this is a nested optimization problem. You maximize over θ, and the result of this is maximized over k. And the result is the best estimate for θ1 hat and k0 hat. Okay, if you're able to find a solution to this double maximization, the value of the goal function is the g, as the same meaning as the g that we found before. So it is the maximum value of s. And this is going to be compared to a threshold h as before. Okay, now the issue is, can we solve this double optimization problem? Well, if we have Gaussian variables, you can. And on the book by Blank, there is an example where they actually do that. So first you see the expression of the CUSUM here. And then in order to maximize that, what they do is they take the derivative with respect to one parameter. In this case, the derivative with respect to mu1, the post-change value of the mean. And this can be solved. This can be solved, and then you get a solution. Well, you do the same also with respect to the change instant. You can get a solution. This is the example, the solution for mu1. The problem is that, again, in general, if you have another distribution, or if you don't know the distribution of your variable, then that's going to be quite difficult. And you can try to solve it numerically. Okay, and this is the second part of the example. So with some difficulty, but pen and paper, you can do it for the Gaussian case. But this is pretty much all that you can do pen and paper. Okay, so we got to the end, and we have seen some advanced, in this series of lecture, we have seen deterministic and probabilistic change detection algorithms, both simple and advanced. And remember that in the probabilistic test, we assume independent samples. In the next series of lectures, we are going to cover signal-based diagnosis.